In this lesson, we're exploring two more trigonometric ratios. We're looking at sine and cosine. And the Explore activity described in your textbook uses geometry software. So you know my favorite geometry software is GeoGebra. So I've embedded this GeoGebra into a page on Canvas. So you have access to this as well, so that if you want to, you can access it and kind of play with the angles and see what happens to the segments accordingly. Unfortunately, there's a difference between how I constructed it and how the book wanted it constructed. You'll see in Reflect number 1, it says drag D along AC, and I can't. If I want to move this parallel line, or this vertical line rather, I need to drag E along AB. So when you see the next part of the video where I'm under the document camera, you'll see that I've edited that accordingly. So in the Explore activity, parts A and B is basically to construct this. So I've already done that. And then it says measure angle A. All right, so here's angle A. I'm going to adjust it so that it's at least kind of a remotely pretty angle. I'm going to make it as close to 30 as I can get. That's about as good as it's going to get. And then measure the side lengths DE, AE, and AD and calculate the ratios in part D of DE over AD and AE over AD. So when I calculate DE over AD, that is 1.17, you see on your screen is the length of DE, and AD is 2.36. And when I calculate that, 1.17 divided by 2.36, that is approximately 0.5. And then when I calculate AE over AD, that is 2.05, you see is the length of AE, over AD, which is 2.36, and that's approximately 0.9. And then you'll see that in the Reflect, they're asking us to drag the point. And so, like I said earlier, I can't drag D, but I can drag E. So I'm going to drag E, and notice that my triangle is now larger. And it says, what postulate or theorem guarantees that the different triangles formed are similar to each other? Well, I constructed it so that this would be a right angle, so I know angle DEA is a 90-degree angle no matter how I move this. Angle A is staying the same, so these triangles are similar by angle. And then it says, as we move this line around, what is happening to those ratios? Okay, so I'm going to bring it over here and calculate that ratio all over again. So again, the first ratio was DE over AD. DE now is 4.2, and when I divide that by AD, 8.46, that's still approximately 0.5, just like it was before. And I'm going to calculate the other ratio, AE over AD. And so AD is 7.34 divided by AD, which is 8.46, and lo and behold, that's still approximately 0.9. So the ratios are staying the same. And why is this? It's because the corresponding parts of the triangles are proportional, so the ratios of the sides are going to stay the same. And as we saw earlier, if I move point C, my angle is changing, and so what's happening to the ratios, well, that's going to be changing. For example, now DE over AD, 1.31 divided by 7.46, well, that's a far cry from the 0.5 that I had earlier. So the ratios are changing as my angle changes. Earlier in this video, I went through this activity and gave a few answers to the questions that were in your Reflect. But if hearing the answers isn't enough for you to jot them down, here are the answers now on your screen. You might want to pause your video to get those down. So the ratios that we were looking at are the length of the leg opposite over the hypotenuse and the length of the leg adjacent over the hypotenuse. And we call those ratios the sine and the cosine trigonometric ratios. In the last lesson, we looked at the tangent ratio, which was opposite over adjacent, and those are both legs. So here now we're bringing in the hypotenuse. So in example 1, part A, we're finding the sine and the cosine of angle D. The sine is the leg opposite angle D over the hypotenuse. Probably the first thing you want to be in the habit of, if you're not kind of automatic with knowing what the hypotenuse is looking at the triangle and noticing where the right angle is, and then identifying the hypotenuse. This is the hypotenuse. Okay, so the leg opposite D is the side that I get, or the side that I land on when I draw a line straight through it. So that's where the 8 comes from. So then the sine of angle D is 8 over 17. This I tend to not use. A similar idea with the cosine. That's the leg adjacent to D. So remember, adjacent is just another word for next to. This is a leg. This is a hypotenuse. I want the leg adjacent over the hypotenuse, so there's the 15 over 17. We're doing the exact same thing in part B, this time with angle F. So leg opposite angle F is the side DE, which is 15, and the hypotenuse is 17. I'm not even going to evaluate that because I don't see any reason to. Cosine of F is adjacent to F over the hypotenuse, and again, that's the most important thing, is these ratios. The 15 over 17, you can evaluate that in your calculator if you want to. I don't see any need to. In reflect number 4, they're asking, what do we notice about the sines and cosines we found? Does this relationship, or is this relationship going to be true for any pair of acute angles? And when we did the tangent video, you hopefully jotted down that the tangent of the two acute angles are reciprocals of each other. Similarly here, the sine of one acute angle equals the cosine of the other. And yes, this is going to be true for any pair of acute angles in a right triangle. In reflect 5, I have a right triangle with triangle PQR. I have the measurements, and it's asking me for the sine and the cosine of P. I would draw the triangle. So I know it's going to be a right triangle. Make sure that you draw a right triangle so that it's very easy to identify what angle is your right angle. I'm told that angle Q is my right angle, P and R. I'm told that PR is 5. QR is 3. I'm asked for the value of the sine of P and the cosine of P. So the sine of P, remember sine is opposite over hypotenuse. I know that the hypotenuse is 5. Oh my goodness, in order to find the cosine, I need to know the length of PQ. Well, it's a right triangle. I know two sides. We've done this before, and here in this chapter, it's tremendously important. Pythagorean Theorem is what I use to find the length of PQ. So 3 squared plus PQ squared equals 5 squared. Remember, it's leg squared plus leg squared equals hypotenuse squared. 9 plus PQ squared equals 25. Subtract the 9 from both sides, I have PQ squared equals 16. And when I take the square root of both sides, I get 4. So the cosine of P is 4 over 5. We mentioned earlier that the sine of one acute angle will equal the cosine of the other acute angle, and they're kind of representing that here. We're introducing the Greek letter theta. You're going to see a lot of that. Maybe not so much in Algebra 2, but if you go further than that, you'll see that Greek letter quite a bit. So in Part A, I'm given that the sine of 38 degrees is 0.616. I want to find the cosine of that complementary angle. All right. So the sine of theta is equal to the cosine of 90 minus theta. So that means that the sine of 38 equals the cosine of 90 minus 38. I know that the sine of 38 will equal the cosine of 52, and that means that 0.616 is the cosine of that complementary angle. Same idea here. I'm given that the cosine of 60 is 0.5. I'm trying to find the sine of the complementary angle. Well, this is true. Remember that the sine of one angle equals the cosine of the other. But let's go ahead and fill in their blanks. I'm going to substitute 60 in. So the cosine of 60 is going to equal the sine of 30. So the cosine of 60 is, they gave it to us up here, it's 0.5 or 1/2. So that's going to equal the sine of 30. So the sine of the complementary angle, is 0.5. What can you conclude about the sine and cosine of 45? So in a right triangle with one 45-degree angle, the other acute angle is also 45. So if I use the fact that the sine of one acute angle will equal the cosine of the other, that means that the sine of 45 degrees equals the cosine of 45 degrees. Is it possible for the sine or cosine of an acute angle to equal 1? Well, let's consider this right triangle. The definition of sine is opposite over hypotenuse. Hypotenuse, remember, is the longest segment of a right triangle. And in order for something over something to equal 1, BC would have to be as long as AB. That's impossible. So the answer is no. A leg cannot be as long as a hypotenuse. Numbers 8 and 9 are the same idea as the last example. If the sine of A equals the cosine of B, and the cosine of B cosine of A equals the sine of B, where A and B are complementary angles. Well, if I know that the cosine of 73 is this, then this has to equal the sine of the complementary angle. So it's 0.292. Here, I'm given the sine of 45 degrees. Well, we already talked about how the sine of 45 is going to equal the cosine of 45. So that's also going to equal 0.707 approximately. Now we're getting to the meat of the lesson, using the sine and the cosine to find lengths in triangles. And in part A, since the x that I'm trying to find is opposite the angle that I'm given, and since I'm given the hypotenuse, I would use sine in order to find the value of x, which is what they did here. So I'm just using the definition. Sine of the angle, that's the 11, equals opposite over hypotenuse. And then they're just solving for x. You must use a scientific calculator. You cannot do this stuff without a scientific calculator. So I'm pulling out my scientific calculator so that I can do the next problem. And in part B, I'm trying to find the distance that the ramp extends in front of the wall. So that's this y. This y, notice, is adjacent to the 11. The 12 is still a hypotenuse. Adjacent over hypotenuse, that's the definition of cosine. So that's why we're going to use cosine to find the value of y. So I'm going to substitute in 11 for A, y for AB, and the length of AC is 12. So cosine of 11 equals y over 12. Multiply both sides by 12, and I have 12 times the cosine of 11 equals y. And in my calculator, when I multiply 12 times the cosine of 11, I get approximately 11.8. So the wrap extends in front of the wall about 11.8 feet. Could we have found the height of the wall using the cosine? Let's look at the diagram. In order to find the height of the wall using cosine, the wall would have to be adjacent to the angle I know. Well, they gave me that this angle is 11, so some of you might be automatically thinking no, but don't forget what you know about the angles of a triangle. You know that the three angles have to add up to 180. So you could do 90 plus 11 and get 101, subtract that from 180, and get that this angle is 79. So, yes, if you find the measure of angle C, in this your turn example, we are finding the length of this ramp Z. Notice the information that's given to us. The maximum angle for the ramp has to be 8 degrees, so notice where they put the 8. The wall, we know, is 2.3 feet. That's given to us in the diagram. So the first thing we have to do is figure out what trig ratio we're going to use. I have this 8-degree angle. This wall is opposite angle A. Z is the hypotenuse. And eventually you're going to memorize these ratios, but for now, maybe you refer back and you look here and you say, okay, which one uses opposite and hypotenuse? And that's sine. So we come back to the problem that we're solving and we set up our equation. Sine of 8 equals opposite, which is 2.3, over hypotenuse. Now remember how we looked at this before when the variable was on the bottom. Remember that you're allowed to switch things in a proportion. You're allowed to switch things across the diagonal. The z and the sine of 8 are across a diagonal from each other. So I know that z will equal 2.3 over the sine of 8. So in your calculator, you take 2.3 divided by the sine of 8, and you get that the ramp is going to be, when I round to the nearest tenth of a foot, 16.5 feet. In the next example, just like what we did in the tangent ratio video, we're going to use the inverse trig ratio in order to find angle measures. So remember, you use the regular sine, cosine, or tangent to find a segment length, but you use the inverse function to find an angle measure. So in example 4, we're writing a trigonometric ratio for angle R. So the 7 is opposite angle R. The 13 is the hypotenuse, so that's why they decided to use the sine ratio. So the sine of R equals PQ over PR. They substituted the values in and got that value. Now we're going to use what we just found to find the measure of angle R. Now the measure of angle R is going to be the inverse sine of that 7 over 13. So in your calculator, you evaluate that 7 divided by 13 and take the inverse sine of it. Depending on what kind of calculator you have, the order of the buttons that you're pushing matters, and we'll talk about that in class. This is 32.6 degrees. And now we're going to find angle P as well by setting up a cosine ratio. So we substitute in 7 for PQ and 13 for PR. So that's 7 over 13, this time as the cosine of P. So that means that the inverse cosine of 7 over 13 is going to be the measure of angle P. So again, I evaluate that 7 divided by 13 and take the inverse cosine this time. And that gives me 57.4 degrees. How else could we have found angle P? We could have used Pythagorean's theorem. Oh no, even easier. 3 angles of a triangle add up to 180 degrees. In this your turn example, we're finding the measure of the angles again. So same process that we did back here. In order to find angle Y, I notice that the 14 is adjacent to Y and that the 23 is the hypotenuse. Adjacent and hypotenuse, that's cosine. So cosine of Y equals 14 over 23, which means that the measure of angle Y is going to be the inverse cosine of 14 over 23. So in my calculator, I evaluate that 14 over 23. I take the inverse cosine of it, and I get approximately 52.5 degrees. And once again, yes, by all means, you could subtract this from 90 degrees in order to get angle Z. However, in the interest of getting the practice, I would advise you use the trig to do this, keeping in mind what you know your answer is supposed to be. All right, so I used cosine to find angle Y. That means I'm going to use sine to find angle Z, because the 14 is opposite angle Z. 23 is still the hypotenuse. So that means that the measure of angle Z is going to equal the inverse sine of 14 over 23. And again, in my calculator, I evaluate that 14 over 23, taking the inverse sine this time, and I get 37.5, which is a reasonable answer, because if I add this to 90, I get 180 degrees.